Hello everyone, I'm Junichi Kurihara. In this lecture, I'd like to talk about optical Earth observation with microsatellites. First of all, let me introduce myself. I'm currently an associate professor at Hokkaido Information University. Prior to that, I worked at Hokkaido University for 12 years. During that time, I was involved in several microsatellite projects. These included Japanese projects and joint projects with the Philippines, Vietnam, and other countries. For example, Radian 2, Diwata 1, Diwata 2, MicroDragon, and RISAT projects. In these projects, I have been involved in the development and operation of optical sensors to be mounted on satellites. My main area of expertise is remote sensing, with particular interest in hyperspectral imaging and Earth observation. Let me introduce the contents of this lecture. The first chapter is an introduction to optical sensors as basic knowledge. Next, I will introduce the history and trends in Earth observation. Next, I will talk about design and manufacture of optical sensors, and testing and control of optical sensors, and then satellite operation and data processing, and on orbit calibration and data management. Finally, I will summarize this lecture with a conclusion. So let's move on to the first chapter on Introduction to Optical Sensors. First, I'd like to review your knowledge of light. Light is a type of electromagnetic wave, and electromagnetic waves are classified according to their wavelengths. Electromagnetic waves with wavelengths shorter than 10 nanometers are called ionizing radiation, while those with longer wavelengths are called non-ionizing radiation. Ionizing radiation includes gamma rays and X-rays. Among non-ionizing radiation, electromagnetic waves with wavelengths from 10 nanometers to 1 nanometers are called light. Electromagnetic waves with longer wavelengths than that include microwaves, radio waves, and long radio waves. Now, among light with wavelengths visible to our eyes is called visible light. It is light with wavelengths of approximately 400 nanometers to 700 nanometers. Light with wavelengths shorter than this visible light is called ultraviolet light, and light with wavelengths longer than this is called infrared light. By the way, interestingly, light has both wave and particle properties. This is called wave-particle duality. The energy of one particle, or photon, is inversely proportional to the wavelengths of light. This is very interesting. This shows that the shorter the wavelengths, the higher the energy. In fact, ultraviolet light has more energy than visible light. Next, let's talk about the light detectors. Light is detected by different types of detectors, depending on its wavelengths. Visible light, which is most familiar to us, is detected by photomultiplier tubes and silicon photodiodes. Silicon photodiodes are used in CCD, charge-coupled device, and CMOS, complementary metal oxide semiconductor, images sensors, in your digital cameras. Infrared light with longer wavelengths is detected by photodiodes using a substance called indium gallium arsenide. For detection of light with even longer wavelengths, special substances called indium antimonide and mercury cadmium telluride are used. However, these detectors cannot be used without cooling. On the other hand, for infrared light with longer wavelengths, a detector called a microbolometer is used, which does not need to be cooled. By the way, light with wavelengths from 3 to 15 micrometers is sometimes called thermal infrared. The thermal infrared detected by these detectors can be visualized as thermography. Let us now compare CCD and CMOS image sensors. Both use silicon photodiodes corresponding to each pixel to convert light into an electrical charge for detection, but there is a difference in subsequent process. CCD image sensors use vertical and horizontal CCDs, or charge-coupled devices, to transfer the electrical charge altogether. At the end of this transfer, there is an amplifier, which amplifies the charge and extracts it as an signal. A CMOS image sensor, on the other hand, has an amplifier connected to each individual photodiode so that the output of each pixel is read out sequentially. This feature can be used to output only the pixels that you wanted read out. Next, we will discuss global shutter and rolling shutter. A global shutter is one in which the timing of exposure for each pixel of the image sensor is the same. This is the case with CCDs, which transfer the stored charge all at the same time. On the other hand, a rolling shutter is one in which the exposure timing of each pixel is different. In practice, the image is read out line by line, so the exposure timing differs from line to line. Both global shutter and rolling shutter are fine when imaging a stationary subject, but when there is a relative speed between the subject and the camera, such as the Earth's surface as seen from a satellite, the rolling shutter will cause distortion in the image. Recently, some CMOS image sensors have rolling shutters, so not all CMOS image sensors distort images, but care should be taken. Next, the format of image sensor is explained. Image sensors come in a variety of sizes, but in general, the combination of the length of vertical and horizontal size is called the sensor size. In contrast, the size of each pixel is called the pixel size. The sensor size is the length of each side of the pixel size multiplied the number of pixels in each side. By the way, there is a small portion of the edge of each pixel that cannot be received light. Also, some pixels on the edge of the image sensor are shielded and cannot receive light. These shielded pixels are called optical black or OB pixels, while other pixels that can receive light are called effective pixels. Image sensors do not detect light of any wavelengths in the same way, and their sensitivity is wavelength dependent. This is called the spectral sensitivity of the image sensor. This figure shows a typical spectral sensitivity graph of an image sensor using silicon photodiodes. In most cases, The sensitivity in the ultraviolet below 400 nanometer is low, with a peak sensitivity between 500 and 600 nanometers, and the sensitivity gradually decreases towards the near infrared. Note that the human eye can only see visible light in the 400 to 700 nanometer range, but these image sensors have some sensitivity in the near infrared as well. Spectral sensitivity of monochrome image sensor was introduced in the previous page, but what about color image sensors? Generally, in a color sensor with 3 RGB colors, red, green, and blue, the 3 color filters are arranged in what is called a barrier filter array, as shown in the figure on the left. Each pixel can only detect light passing through that filter. The graph on the right shows the spectral sensitivity of each pixel. You can see that each pixel has a peak at the wavelength that represents its color. A color sensor detects light of 3 colors in 4 pixel units. But that does not mean that number of pixels is reduced to a quarter. For example, if we focus on the blue pixel, the other 2 colors of light at this pixel location, red and green, cannot be detected by this pixel, but can be interpolated from the light intensity detected by the surrounding red and green pixels. In this way, the light intensity of 3 RGB colors can be obtained for all pixels. Now that we have finished with the basics of detectors, let's move on to the top optical sensors as a whole. An optical sensor consists of 3 main parts, from left to right. There is a light collector, such as a lens or a mirror that collects incident light, the spectrometer, such as a filter or prism, and the detector, such as an image sensor. The light collector and the spectrometer together are sometimes referred to as the optical system. A spectrometer may also include a detector. Light detected by the detector is converted into an electrical signal and sent to the data handling unit. There are 2 main methods of light collectors. These are refractive and reflective optical systems. Refractive optical systems use lenses to collect light. In contrast, reflective systems use mirrors, such as concave or convex mirrors, to collect light. The advantage of a refractive system is a wide field of view. The advantage of reflective type is that it pulls back the light rays, making it more compact than reflective type. Also, there is no chromatic aberration, which is a difference in refractive index depending on the wavelength of light, resulting in a failure of a lens to focus all colors to the same point. In fact, many hybrid optical systems combining refractive and reflective optics have been devised. The next section discusses spectrometers. Typical spectral elements are prisms and diffraction gratings. Prisms transmit light and diffraction gratings reflect light. But in doing so, both work to disperse light according to the wavelengths. Filters, on the other hand, allow only light of a specific wavelength to pass through. There are a variety of other optical elements as well. Optical sensors are classified into several types depending on the spectral range and the spectral resolution to be measured. The most familiar is a color sensor. Color sensors measure only the 3 RGB colors, while those with 4 or more colors are generally called multispectral sensors. Many multispectral sensors can measure several bands of near-infrared in addition to visible light. Most optical Earth observation satellites are equipped with these multispectral sensors. Sensors that continuously measure an even wider range of wavelengths in tens to hundreds of colors are called hyperspectral sensors. Hyperspectral sensors are challenging for small satellites because they require advanced technology not only for manufacturing, but also for operation. Finally, an optical sensor that differs slightly from other sensors is a thermal infrared sensor, sometimes simply referred to as thermal sensors. This is also difficult to install on a small satellite if it requires cooling. As an example, let me introduce you to the world's most famous Earth observation satellite. It is Landsat series with a history of over 50 years. The multispectral bands for Landsat 1 through 9 are shown below. The 4 bands marked MSS at the bottom are the bands of the multispectral scanner on Landsat 1 through 5. The TM bands, second from the bottom, are for the semantic mapper on both Landsat 4 and 5. Short wavelength infrared and thermal infrared bands have been added. Third from the bottom is ETM Plus on board Landsat 7. Here, for the first time, a band called panchromatic, which covers a wide range of visible to near-infrared wavelengths, have been added. At the top of the OLI and TRS bands installed on the Landsat 8 and 9, which are currently in operation. The number of bands has now increased to 11. One of the key performance features of optical sensors is the field of view and spatial resolution. Both can be determined with a simple calculation if the altitude of the satellite is known in addition to the focal length of the optical sensor and the specifications of the image sensor. The field of view is an angle and is not related to the altitude of the satellite, while the spatial resolution decreases with the altitude of the satellite. Spatial resolution is also called ground sample distance, or GSD for short. Most Earth observation satellites take a sun-synchronous orbit. This is because they pass over a point on the ground at the same time throughout the year, making it very convenient to study changes in the Earth's surface. The time of day is often chosen to be around noon, when the sun is high in the sky. Small satellites do not have the opportunity to choose their orbit, but they are lucky if the large satellite being launched with them is an Earth observation satellite, because it may be in the sun-synchronous orbit. At the end of this chapter, we will also discuss imaging methods. More than 90% of Earth observation satellites use a method called push-broom imaging to image the Earth's surface. In this method, the instantaneous field of view of the optical sensor faces nadir to the satellite, directly below. in a low perpendicular to the satellite's direction of travel. As the satellite travels at a constant speed, it scans the Earth's surface as if it were a copying machine. On the other hand, a method that is increasingly used for small satellites is the two-dimensional imaging method. In this method, a snapshot of a certain location is taken, just like a camera. The advantage of two-dimensional imaging is that the amount of data can be reduced by limiting the locations where images are taken. This is ideal for small satellites, which have limited data transmission. The next chapter is about the history and trends in Earth observation. First, let us summarize the size of small satellites again. Since the size of a satellite is roughly proportional to its weight, it is generally classified by weight. A satellite heavier than 1,000 kilograms is called a large satellite, and a satellite lighter than that is called a small satellite. Small satellites are further classified into mini, micro, nano, and picosatellites based on their weight. A 1U and 3U CubeSat is nanosatellite, and a 6U and 12U is a microsatellite. Now, the larger the satellite, the longer it takes to develop. While many large satellites take more than 10 years from the start of the planning to launch, small satellites can be developed in just a few years. This short development life cycle has a significant impact on the speed at which technology evolves. The cost of development is also an order of magnitude lower for small satellites. Small satellites are innovation that will make space development faster, better, and cheaper. By the way, spatial resolution, one of the most important capabilities of Earth observation satellites, has improved over time. For example, the spatial resolution of Landsat-1 MSS launched in the 1970s was 80 meters, but this was reduced to 10 meters in the 1990s. And some satellites now have a spatial resolution of less than 1 meter. In the 1970s, we could not even distinguish individual houses, but now we can distinguish even the smallest features, such as whether a house has a chimney. This has completely changed the type and value of information that can be obtained from satellite imagery. This figure maps the spatial resolution and spectral bands of Earth observation satellites launched to date. Note that the vertical axis is the spatial resolution, and the horizontal axis is the number of bands, but on logarithmic scale. The satellites are depicted by circles. The size of the circle represents the weight of the satellite, and the color represents the age of the satellite when it was launched. What can be seen by looking at this is that the satellites have become smaller and the spatial resolution has increased with time. In addition, the number of bands has increased in recent years since the era when 4-band satellites were mainstream. Thus, not only spatial resolution, but also the number of bands has changed over time. This illustration depicts a constellation of large Earth observation satellites called A-Train, built in the 2010s. Satellites equipped with different observation sensors were put into a sun-synchronous orbit a few minutes apart. Some of these satellites are still in operation today. It was a great idea and the result of international cooperation, but because of satellite launch failures, it took almost 10 years after the launch of the first satellite to complete the constellation. One of the satellites was out of service before it was completed. No similar constellations have been planned since then. This shows that large satellite constellations are very difficult to achieve. Furthermore, the same location can only be observed once every 16 days. Then came the era of nano-microsatellite constellation. Today's planet's 3U CubeSat Dove has more than 200 satellites in orbit. This means that satellite images of every location in the world are now available in every day. Dove's field of view is much narrower than that of large satellites, but the number of satellites makes up for that disadvantage. Furthermore, Dove's observation performance was evolved. The first generation of Dove had only 4 bands, while the third generation of Dove has increased the number of bands to 8. This rapid evolution is another advantage of nanomicrosatellites. CubeSats are currently being developed around the world. For example, a project is underway to detect volcanic eruptions on board ESA's 6U CubeSat, PISat, using deep learning from images taken. In this way, it is becoming possible to compensate for one of the weaknesses of nanomicrosatellites, namely their low communication capacity. The next chapter is about the design and manufacture of optical sensors. I will now give you an example of a specific mission. In the field of ocean color remote sensing, research is being conducted to find some suitable locations for aquaculture based on satellite observation images of coastal areas. For example, as shown in this figure, it is possible to use satellite observation to assess the sea area suitable for scallop aquaculture on the coast of Hokkaido, Japan. One substance that is currently attracting attention in the field of ocean color remote sensing is called color dissolved organic matter, or CDOM for short. This substance is discharged into the ocean in large quantities from rivers flowing through the heatlands in Southeast Asia and other regions, and has a significant negative impact on coastal aquaculture. In addition, as shown in the figure, CDOM has a property of strongly absorbing ultraviolet rays. Therefore, by observing in the near ultraviolet wavelength range, we can determine the amount of this substance and assess its impact on aquaculture. Therefore, the observation requirements for this CDOM-targeted ocean color remote sensing are summarized in this table. The wavelength range is in the visible near-infrared region, including the band from 400 to 430 nanometers, and the field of view can be narrower since it is a coastal area. The key here is the spatial resolution. There have been no high spatial resolution observation targeting the CDOM. Observation should be made around 10 a.m. The reason for selecting that time is that when the sun is high in the sky, the reflection of sunlight from the sea surface hinders observation. Based on this observation requirement, we designed an optical sensor called the Ocean Observation Camera, or OOC, and installed it on the LiDSat microsatellite. The OOC is a 4-band multispectral sensor with 4 independent cameras with different bandpass filters. Now, let's list some important points to design. First is how to choose the detector. You need to choose the type of image sensor, CCD or CMOS. Then you choose the size, sensor size, and image size from a variety of formats. Another important thing is the space provenance. In the end, we choose the space proven Vertex T065 CCD image sensor for OOC. The next question is how to select the lens. Determining the focal length determines the FOV and the spatial resolution. Here, the spectral range also needs to be considered. This is because commercially available lenses may not be compatible with the near-infrared region. Finally, find out if customization is possible. It may be necessary to have the grease used inside the lens removed by special order. This is to prevent the grease from volatilizing in space and contaminating sensors and satellites. In the end, we choose a Monitex ML5018 lens. However, we did not select the detector and the lens separately. We carefully considered the characteristics of both. Next, a bandpass filter was selected. In doing so, the center wavelengths and bandwidth must match the observation requirements. Peak transmittance is also an important factor. Also, if a wide wavelength range is to be observed, as in this case, the blocking wavelengths are also investigated. Particular attention should also be paid to optical density, especially if the bandwidth is narrow. We carefully choose 4 bandpass filters because these were the most expensive components in this sensor. Chapter 4 considers testing and control of optical sensors. The most important test for optical sensor is focusing. A special device called a collimator is used for this purpose. A collimator is a device used to parallel the rays of light emitted from a light source through the pinhole. This produces the main effect as placing the light source at the infinity. The focus of the sensor is adjusted so that the image of the light source is minimized. The photo below shows the actual focusing process. A mirror is used so that the focus can be checked even after the sensor is mounted on the satellite. The next most important test is laboratory radiometric calibration. Some radiometric calibrations are performed in orbit after launch and are discussed in the next chapter. In laboratory calibration, an integrating sphere is used to create a light source of homogeneous brightness, which is then measured by an optical sensor. Since optical sensors have non-uniform sensitivity due to the optical system and detectors, the brightness of the captured image will not be uniform, even if a homogeneous light source is captured. Conversely, this measurement allows us to measure the non-uniformity of sensitivity. Based on the calibration data, images taken after the launch can be corrected using radiometric techniques to improve the quality and accuracy of remote sensing images. Now, optical sensors, like other onboard devices, must undergo various environmental tests. These include vibration, shock, thermal, vacuum, and radiation tests. Please refer to other lectures for more information. From here, I'd like to talk about the data processing. Optical sensors are connected to a data handling unit, or DHU for short, that processes the data. This DHU not only processes the data from optical sensor, but also controls the optical sensor itself. The DHU is also connected to the attitude control system, which timestamps the image with information on satellite's position and attitude at the moment the optical sensor acquires image. The image data with various supplementary information, which is called ancillary data, is sent from the DHU to the communication system without going through the onboard computer, OBC, to avoid overloading the OBC, and is then sent to the ground. By the way, two types of memory are generally installed in DHUs. One is the volatile memory, and the other is non-volatile memory. Volatile memory can be read and written at high speed, but the stored data is lost when the DHU is turned off. On the other hand, non-volatile memory is slower to read and write than volatile memory, but the stored data is not lost when the power is turned off. Therefore, image data that the optical sensor acquires in the large quantities in a short period of time can be stored once in the volatile memory and slowly move to the non-volatile memory until the power is turned off. Once stored in non-volatile memory, the data can be sent to the transmitter by restarting the DHU at an appropriate time. In the next chapter, chapter 5, we'll take a closer look at the satellite operations and data processing. Even after satellite is completed, there is still much to do. First, we hand over the completed satellite to the company or agency responsible for its launch. At that time, the satellite will undergo an inspection. Once the satellite has been successfully delivered, all that waits is launch. This period between the completion of a satellite and its launch is very important. This period is a good opportunity to review the operation plan for the optical sensor. Because after the launch, there is no such time to take this review. Immediately after launch, the commissioning phase of the satellite begins. And after that is cleared, the nominal operation phase begins. Here are some notes on the commissioning phase. The first priority is to check the power, communication, and other function of the satellite bus system. Optical sensor operations are checked after the satellite's course attitude control is established. Do not be in a hurry. Check the critical functions of the optical sensors one by one, starting with the most important ones. That is power on, off. Second, check the housekeeping status, including voltage, current, and temperature. Then check the capture of images. Include checks if the exposure time and gain can be changed. check the memory storage. Then check the data downlink communication. Note that the same procedures and commands should be used for these checks as were done on the ground prior to launch. If problem arises during the commissioning phase, first carefully check for differences from the pre-launch commands, status, and procedures. You should also suspect that the pre-launch data or records may be incorrect. If you still have engineering model equipment on the ground, try to reproduce the experiment using it. You should also consider the possibility that problems were caused by the transportation or launch of the satellite. Then, if possible, share the valuable lessons learned with the community. The differences between the commissioning phase and the nominal operation phase include the length of time, the concentration of human resources, and the status of members. You need to be aware of the possibility of changing circumstances, not only for satellites, but also for those who operate it. During the commissioning phase, the documentation and automation of operational procedures is very important. From here, we consider the data processing level. Observation data from optical sensors of each Earth observation satellites are processed in several levels. The definition of data processing level is almost the same for all Earth observation satellites. The first, unprocessed data is called level 0. Ancillary data is added to this data, which is called level 1A. The first radiometrically and geometrically collected data is called level 1B. Atmospherically collected data is usually referred to as level 2. Consider the processing of level 0 or L0 data. Satellite data is typically packetized. Therefore, we need to depacketize it. However, some packets of data sent from the satellite may be lost. If none are lost, this should be stored as complete level 0 data, L0C. If some packets are lost, check to see if there were any other similar data. If there is no similar data, save this as partial level 0 data, L0P. If there are other L0Ps, merge them to complete the lost packets. The image on the right shows L0C data merged from the two L0P data. The red color corresponds to the lost packet. Next, we will discuss processing of level 1 and higher level data. Level 1A data is created by adding ancillary data to the L0C data described earlier. Radiometric correction is then applied to this data based on the calibration data. If the data was taken looking in the rear, then geometric correction is applied. If not, automatic georeferencing can be performed using existing satellite data. The image on the left shows the georeferencing using image matching with an existing satellite image. This is how L1B data is created. To perform atmospheric correction, a model called the radiative transport code must be used, and the resulting data is L2 data. Chapter 6 presents on orbit calibration and data management. There are three methods of calibration in orbit. One is on-board calibration. In this method, calibration equipment such as lamps and solar diffusers are mounted on satellites. However, these calibration devices themselves may be deteriorate during launch or from aging, and it is difficult to install them on a small satellite. The next method is vicarious calibration. In this method, a ground target with no radiometric properties, such as desert, is observed. However, simultaneous observation on the ground are required. Also, there are uncertainties due to the atmospheric corrections. The last method is lunar calibration. Lunar observations are free from atmospheric effects, and changes in lunar reflectance over time can be ignored. Observation opportunities occur twice a month, before and after the full moon. The accuracy depends on the lunar reflectance model used. This method is suitable for small satellites, but on the contrary, large satellites cannot observe the moon with high frequency. Suitable target sites for vicarious calibration are highly reflective, isotropically diffuse, and spatially homogeneous ground surfaces. A high frequency of clear skies and a dry atmosphere are also required. Such vicarious calibration sites on Earth comprises a radiometric calibration network called RADCALnet, which is operated by the Committee on Earth Observation Satellites, CEOs. Data from each site is collected, processed, and published on the Internet. The first requirement for lunar calibration is that the phase angle must be greater than 7 degrees before and after the full moon. If the moon is perfectly within the field of view of the optical sensor, a lunar reflectance model called the RORO model can be used. If the moon only partially fits in the field of view, the SP model can be used. The image below shows a comparison between the moon taken by ocean observation camera on board the LISAT microsatellite and the simulation using the SP model. There are also various problems related to the management of observation data. First, there is the issue of security. Japan has a law called the Satellite Remote Sensing Law, which must be observed. Second, there is the issue of reliability. As described in chapter 5.2, there are various data processing and data processing levels. In addition, on-orbit calibration was introduced in chapter 6.1. The third is the issue of availability. Automation and efficiency of data processing were discussed in chapter 5.1 and 5.2. In this section, we discuss management system of observation data. We have developed the Satellite Data Manager, SDM, to manage satellite observation data. This system automatically processes observation data downloaded from satellites and manages them visually. It displays an interactive map on the browser showing where on the globe the observation data was taken. You can also click on the icon to open and view this image. The system is entirely based on the open source libraries, making it easy for universities and research institutes developing a CubeSat to use. Finally, a conclusion. When designing an optical sensor, it is necessary to carefully examine the optical characteristic of observation target and select the optics and detector suitable for the observation. When installing an optical sensor on a small satellite or CubeSat, it is necessary to conduct tests to confirm its optical performance in addition to environmental tests. Even for small satellites or CubeSats, observation data from optical sensors are large, so it is advisable to plan data processing and management well in advance in their launches. This concludes my lecture. Thank you very much.